Let's get started. I'm going to talk about quality solutions for battery cells. We all know the global energy needs, and there are different solutions out there. We have here about some of those solutions, and you guess well, batteries is the main topic, which are supposed to charge our lives in the future. There are some challenges still with batteries, and that's why researchers continue to investigate new energy batteries, because we need not just usual batteries, we need some superhero batteries. Batteries that are last longer, that are safer and cheaper. And we ideally want those new materials to get into new battery devices that power our lives without making us broke. So let's charge into this topic and see what electrifying ideas we can spark today. When we speak about batteries, it's an interesting system because it goes through a series of scales going all the way from nanometers to centimeters scale lengths. And speaking of safety, we are familiar with the typical issues. We hopefully don't want this to happen to our cars. That would be really catastrophic. So that's why we need to do investigation or quality inspection of those batteries, either by sampling at line or ideally in line. From the other thing is, the batteries, we don't want to open the battery, so ideally we want to do a non-destructive testing kind of system. From the different type of systems that are out there, or technologies, including ultrasonic or even light microscopy. X-ray microscopy, I would say, is the only one that covers the largest range, all the way from nanometers to centimeters or even higher, with different technologies potentially. And it has the penetration power to get into that. If you look at other technologies like ultrasound, yes, it can see inside, but the resolution is not that high. On electron microscopy, the resolution is very great, but then you have to prepare the sample. And light microscopy, you only can see in the outside. And you can see in that plot over here, which you can further consult in the resolution, the type of features that you can see inside of a battery at those different feature lengths. Going a little deeper into the X-ray, we can call two types of technology: 3D X-ray microscopy or X-ray CT. X-ray CT can go all the way to battery packs, as you can see in this slide, or a 3D X-ray microscopy to investigate battery materials. These are some types of features that you can see inside of batteries with CT. And this is one of the typical workflows. And now I'm going deep into the X-ray microscopy, when you collect different radiographs in the orders of thousands or so to create a 3D reconstruction, and then go with a virtual software to see inside without having to cross-section the battery. This technology involves some additional components like optical magnification that you don't get in traditional micro CT. This is an example of a 650 lithium-ion battery, and you can see two different scans, one in a large field of view where you can see some features but not at the resolution that you might want, and then you can use one of those zoom-in lenses to get into a further interior region of interest. Of course, the field of view is a little bit limited, but then you can see particles and you can see gaps and other things that you could not see otherwise. And all of this is being done non-destructively. In fact, you see here a portion of another type of battery that has been scanned, but the full battery can scan at a low resolution, then zoom in into different regions of interest until you get the features that you want to resolve. In this case, you see a crack there that has been reconstructed. And this is the typical workflow. So you go from the full battery, in this case it is a 21700, into regions of interest, And you can see not only at high resolution, but at high contrast, low density materials and high density materials. And of course, this is not only for automotive, it's also for electronics, and because you have the three-dimensional data, you can create all kind of videos and see after several cycles of charging and discharging how the battery degrades. And you can see here some traces of delaminations, for example. So again, the advantage of 3D X-ray microscopy is that you can use those zoom-in lenses to get into different field of view and zoom in into higher resolution. And then you see all kind of features, low density, high density, and the 3D X-ray microscopy, I would say, is the only technology that can go to the particle level in all the X-ray technologies that you can see out there. And evaluate traces of delamination, as you can see here. I have been mentioning charging and discharging, and this is very typical for researchers. They scan a fresh battery. You can see that there are some anode materials there, bright, and in the H battery 200 cycles, it has disappeared. So if you scan that in the intermediate cycle, then you can see that that particle is degrading and actually being consumed after several cycles of charging and discharging. And this is very important and telling a story for all the researchers out there. Not only you want to see inside, you want also to see morphological details, which are important because you don't want the different anodes to deflect and touch each other because of the catastrophic events that it could happen. And one of the things with the X-ray CT, which can be considered slow, is we want to go faster. And we want to do it faster because of the demands of the battery manufacturers. So we have developed some technologies that can scan a little faster by doing continuous rotation when you are collecting the 3D radiographs, but also integrating deep learning technologies that can cut the number of projections that you can collect to be able to get rid of noise and get high quality data with, let's say, hundreds of projections instead of thousands that you would need with traditional way of reconstructing. Let me show you an example. This example shows you a slide with more than 3,000 projections with the traditional way of reconstructing. If you start cutting projections, then you start seeing artifacts, and that's a problem. But if you create a model that can get rid of what is noise or read the aliasing artifacts from reducing projections, you get rid of it, and you now see the features without problem. And that's how we are integrating deep learning into the reconstruction algorithms for X-ray microscopy. And if you don't care about time, you can scan really high quality data that you can recognize features that you wouldn't do otherwise because there is a lot of noise. But those features are very important to enter into simulation packages when you are trying to create the porosity map inside of those batteries or so. So until here I have been talking about technologies that you can use for 3D X-ray inspection of batteries, but what happened at the end of the life? At the end of the life, if you want to recycle your batteries, then you get something that is called characterization of black mass. And the nice thing is you could use this technology to characterize that black mass material. It is a full cycle of when you are trying to recycle lithium-ion batteries, and what we call black mass is just that chunk of material that is left after the recycling. Yes, you can use the same technology and especially use the deep learning algorithms, Deep Recon Pro, which we call it, and Deep Scout for different functions, for speeding the reconstruction or improving the resolution in a large field of view. And after that, you can do quantification. You can do this traditionally with a 2D SEM when you have the sample, but the problem is you have just 2D information. In here, you take the advantage of getting 3D information, so you have the data in a volume. And once you have that, you can do all kind of quantification, and especially if you use deep learning algorithms that enhance the data and can allow you to see details that you won't see in the traditional way of reconstructing, to now do 3D mapping similar to what you would do with an SEM electron microscope, now in 3D with the X-ray microscope. And then quantify and identify the type of materials that are in this, that are left in this black mass. And you can create all sorts of tables or simulations if you want, or a rotation of the 3D volume of this map. Because you already have the algorithm trained, you don't have to train a new algorithm, you just bring a different block or black mass and you just run this algorithm. So this is going to speed your process because you can just reuse the algorithm that has already been trained. So this is a little bit of a summary of what you can do with black mass, but let me try to go to the end and summarize in a few bullet points what I have presented today. So the first one is I have emphasized quite a lot in the need for doing non-destructive inspection of batteries. We know the dangers of trying to open a battery and create a potential hazard or a fire. With X-ray CT, we can scan battery packs or battery cells, but when you do resolution at a distance with those optical lenses, then you can zoom in with the different lenses in different field of view and see the interior or the inside of intact batteries at really high resolution. So that's the first thing. The second one is you can do this not only for the battery materials, you can do that for finished cells, not only coin cells, but also pouch cells, cylindrical cells, or even battery packs with X-ray CT. Of course, there would be a compromise between resolution and field of view, but then at that level of manufacturing, you only care about large scale features. So actually those two technologies complement very well. If you start with 3D X-ray microscopy to develop your materials, and X-ray CT when you are already in the process of manufacturing cells at speed. And the last portion of the talk was, what do we do with the end material after recycling? Can we identify what is inside with this black mass? And the answer is yes, we can use those same technologies to create a 3D reconstruction, especially using the deep learning algorithms that are going to enhance the data and see clearly the difference between the different gray levels to try to characterize what is inside in terms of components, quantity, or density of the material. And with this, I think I let you go free or ask any questions you might have. Questions?
Any questions for the professor?
It's the last presentation, so you can ask whatever you want. I don't have constraints of time. If not, see you at the reception, enjoy your dinner, and maybe a couple of drinks.